In the wild, it's all about survival. And at the heart of it all is this constant dance between predator and prey. But what actually keeps this whole system from collapsing? Well, today, we're going to explore the surprising truth about ecological stability, and let me tell you, it's way more dynamic than you probably think. Let's dive in.
So let's start with a really fundamental question. When we hear the word stable, we usually picture something, well, flat, unchanging, a predictable straight line. But is that what's really happening out there in nature? We're about to find out that true stability is actually a moving target.
All right, so here's our game plan. We'll kick things off by defining what ecological stability even is. Then we'll get into the classic predator-prey model, the textbook version. After that, we'll look at 3 different states of stability we actually see in the real world. And finally, we'll uncover the key factors, the rules really, that allow these species to coexist over the long run.
Okay, first up, let's really break down what we mean by stability. It's time to move way beyond that simple idea of a flat line.
You see, in ecology, stability has a very specific meaning. It's all about a system's ability to bounce back after it's been knocked around a bit. It's about keeping populations within certain limits, not booming out of control and not crashing into nothing. And of course, the big one, avoiding extinction altogether.
And this right here is the absolute core idea to get your head around. Stability is not the absence of change. Not at all. A stable system is constantly fluctuating. The key difference is that those fluctuations are bounded. They oscillate within a certain range, and they don't spiral out of control.
So, how do we even begin to model these ups and downs? Well, that brings us to the famous theory that first described this ecological dance, the Lotka-Volterra model.
This model lays out this beautiful, predictable cycle. It goes like this. First, with tons of food and not many predators around, the prey population explodes. All that food then allows the predator population to increase, right? But more predators means more prey get eaten, which causes the prey population to drop. And finally, with less food to go around, the predator population crashes too, and the whole cycle starts right back up again.
Now, if you look at a graph of this, you'll spot something really critical. The peak of the predator population always happens after the peak of the prey population. This lag is everything. It's the built-in delay. It's the time it takes for the predators to convert all that extra food into more offspring.
The classic Lotka-Volterra model predicts these very neat, very perfect oscillations. They're perfectly periodic, repeating at exact intervals. The amplitude, so the height of the peaks and the depth of the valleys, it stays exactly the same. They don't shrink and they don't grow over time.
But, that perfect model is just our starting block. Let's bridge that gap between the clean theory and the messy reality by looking at 3 totally different states of stability.
So this first state, neutral stability, is pretty much what that classic Lotka-Volterra model describes. Imagine a ball on a perfectly flat table. If you push it, it just rolls to a new spot and stays there. It doesn't roll back. In this system, if something disturbs it, it doesn't return to its original cycle. It just starts a new one from a different point. It doesn't crash, but it doesn't recover either.
Now this is what we're talking about. Asymptotic stability is way more robust, and it's what we actually see in nature. Here, the oscillations get smaller over time, kind of like ripples in a pond that slowly calm down. When this system gets disturbed, it actively works its way back to its original equilibrium point. That's true resilience.
And then we have the other end of the spectrum, a totally unstable system. Think of a ball balanced on top of a bowling pin. Any little nudge, and it's gone. Here, any disturbance causes the oscillations to get bigger and bigger. The peaks get higher and the troughs get lower, until, inevitably, one of the populations crashes to zero. Extinction.
This brings us to a really crucial point that often trips people up. That neutral stability from the classic model is a cool idea for a perfect theoretical world, but it is not what gives you long-term stability in nature. Real systems need that ability to recover, which is the signature of asymptotic stability.
So what is it that creates that real, resilient, asymptotic stability? Well, obviously, nature is a lot more complex than a simple math equation. Let's get into the real-world factors that change the dance.
Okay, a massive factor here is the predator's functional response. It sounds complicated, but it's just about how a predator's feeding rate changes as the amount of prey changes. A type 2 response can be really destabilizing. The predator is just so efficient, it can keep hunting the prey even when numbers are low, potentially wiping them out. But a type 3 response? That's stabilizing. When prey numbers get really low, the predator might switch to a different food source, or maybe the prey just gets harder to find. This gives the prey a refuge, a chance to bounce back.
And honestly, this is a huge insight. That ability for prey to find safety in low numbers, which is what the Type 3 response is all about, is one of the most powerful forces out there promoting stable, long-term coexistence. It's a real game changer.
Another absolutely critical stabilizing factor is the prey's carrying capacity. I mean, in the real world, prey can't just reproduce forever. They're limited by food, space, resources. This brings in something called density dependence. It naturally slams the brakes on prey growth, which prevents those wild, out-of-control swings and leads directly to those more realistic, damped cycles we're looking for.
Okay, let's bring this all home. In this last section, we're going to synthesize all these ideas into a clear set of rules for how predators and prey manage to stably coexist.
So what's the magic recipe for stability? Well, it's a mix of things. You need those prey refuges that lead to a Type 3 response. You absolutely need density dependence to keep prey growth in check. It also helps a lot if predators aren't ridiculously efficient and if the environment itself is complex, with lots of places for prey to hide.
This table right here is basically the perfect cheat sheet for this whole explainer. The classic Lotka Volterra model, that gives you those theoretical neutral cycles. You add in realistic prey growth, and boom, you get stable, damped oscillations. A super efficient Type 2 predator is bad news, destabilizing, but a Type 3 response, that's a powerful stabilizing force.
And just because these concepts can be a little slippery, let's run through a few common traps to avoid. First, don't assume that just because you see oscillations the system is stable. Remember, those amplifying ones lead straight to extinction. Second, don't mix up that theoretical neutral stability with true resilient stability. And finally, never, ever forget the predator lag or the huge role of the functional response. They're the keys to the whole kingdom.
Look, if you remember just one thing from all of this, let it be this. Real-world predator-prey stability boils down to density dependence and the predator's functional response. Those are the two factors that create the resilient, damped oscillations that allow this dance to go on.
So in the end, this incredible, endless dance between predator and prey, it isn't about finding some kind of perfect, static balance. It's all about a dynamic process. The stability we see in nature isn't a sign of stillness. It's a testament to the incredible resilience that allows the dance to continue, generation after generation.